This is GARIS Essays, that is 2-3 page opinion pieces on topics such as species dominance, the global state, politics, femtotech, religion, society and education. Written by and read aloud by Prof. Dr. Hugo de GARIS. This is essay number 36, entitled SIPI, that's S-I-P-I, which stands for Search for Infra, that means within, Search for Infra Particle Intelligence. Changing the search for non-human intelligence paradigm from outer space to inner space, by Prof. Dr. Hugo de GARIS. Email profhugodegaris@yahoo.com. Website profhugodegaris.wordpress.com. Abstract, I'll make it a bit bigger. This essay is a tight sequel to the author's previous essay, Femtotech, computing at the femtometer scale using quarks and gluons. It applies the same kind of ideas to the attometer, 10 to the minus 18 of a meter scale, using the weak force particles W plus and W minus to create an attotech. The hypothesized SU5 force particles of the grand unified theory, X and Y, are thousands of times heavier than the W particles, and hence operate at the zeptometer scale, 10 to the minus 21 meter, allowing a potential zeptotech. One can generalize from all these techs to create the specifications for an X-tech. The major point of this essay, however, is to claim that looking extraterrestrially for signals from hyper-advanced civilizations far older than we are may be misguided. Perhaps we should be looking inside elementary particles, because creatures constructed at these tiny scales would operate hugely faster, at far greater densities, and with vastly superior performance levels. We may need a paradigm shift away from outer space to inner space, from SETI, that's Search for Extraterrestrial Intelligence, from SETI to SIPI, S-I-P-I, Search for Infra Particle Intelligence. 1. Introduction. In my essay, Femtotech, computing at the femtometer scale using quarks and gluons, I found, in principle, ways to use the properties of quarks and gluons to compute at the femtometer scale. The basic ideas were to store a bit using the color charge on a quark. For example, the red color charge for a 1 and the blue color charge for a 0. Gluons, having two colors each, e.g. a red anti-blue or a blue anti-red, could be used to change the color charge of a quark. That is, it could flip the bit from a red to a blue, that is, from a 1 to a 0, and vice versa. By sequencing the emission and absorption of appropriate color-changing gluons, I was able to map the 3 basic logic gates of classical computing, not, or, and, into corresponding QCD, that's quantum chromodynamics, phenomena, that is, the appropriate behaviors of quarks and gluons. I then wondered if I could do much the same at the next size scale down, that is, at the attometer, 10 to the minus 18 of a meter, using the weak force particles W and Z. As usual, I went hunting through my particle physics texts and found a way to do this too, in principle. Here's how it might be done. 2. W plus and W minus, weak force particles and interactions. The force particles of the weak nuclear force, W plus, W minus and Z0, have very limited range, typically of the attometer scale, 10 to the minus 18 of a meter, and they have mass. In fact, they are considerably heavier than the proton, that is about 2 orders of magnitude heavier. I concentrate on the W particles, since I won't be using the Z particle, which is uncharged. The W particles come in 2 forms. One is positively charged, W+, that is, it has 1 unit of positive electronic charge, and the other is negatively charged, W-, that is, it has 1 unit of negative electronic charge. These weak interaction particles differ from their massless cousins, the photon and the gluons, that mediate the electromagnetic and the color, that's strong nuclear, forces respectively. The gluons only interact with particles that have the color charge, red, blue or green. but take no part in the weak interactions. The gluons thus have no effect on the leptons, that is the light particles such as the electron, the neutrino and their cousins, but react only with hadrons, that is heavy particles such as the baryons, in other words protons and neutrons, etc., that are constructed from 3 quarks, and the mesons, pions, etc., that are constructed from a quark and its antiquark. The weak interaction particles, however, are more universal. They can interact with both hadrons and leptons. So from a future technologist's point of view, there may be more scope for a technology based on the weak force particles than on the color force particles, because the former offer more scope. However, there is a considerable downside with the weak interaction particles, and that is their interaction speed, as you will see later in this essay. The weak particles have another feature that the gluons do not have, and that is that they can change the flavor of a quark, whereas a gluon can't. The flavor of a quark is its type, that is, one of the following set of 6, up, down, strange, charm, top, bottom. A gluon can only change the color charge of a quark, not its flavor. For example, a W plus particle can interact with a down-flavored quark, which has minus a third of the charge and electron, and convert it into an up-flavored quark, which has plus 2/3 of the charge and electron. This reaction, actually an absorption of a W plus, can be represented as follows. W plus acts on a down quark, converts it to an up quark. That is, the W plus acts on the down quark to convert it to an up quark, or the down quark absorbs the W plus and becomes an up quark. Call this process the absorption of the W plus. There is a corresponding emission process of the W plus, which goes as follows. An up-flavored quark collides with a hadron, which is ignored, and splits into a down-flavored quark and a W plus. This reaction can be represented as follows. So an up quark becomes a down quark and a W plus. Note that in both the W plus absorption and the W plus emission processes, the total charges before and after the interactions are conserved. For example, in the W plus emission process, the charge of the up quark equals the charges of the down quark and the W plus. That is, plus 2/3 equals minus a third plus 3/3. The above absorption and emission processes have corresponding equivalents for the W minus weak force particle. The absorption and emission processes can be represented by the following 2 equations. W minus acts on an up quark, turns it into a down quark, and a W down quark emits an up quark and a W minus. We now have the necessary tools to create computation at the attometer scale, because we can emit a W plus or a W minus at will, and use it so that it can be absorbed to change the flavor of a quark from up to down, or from down to up. That is, we can change the bit on the quark. For more on this, see the next section. 3. Computing with quark flavors and the W's. At this point in this essay, if you have not already read my earlier essay, Femtotech, Computing at the Femtometer Scale Using Quarks and Gluons, I strongly advise you to do so, otherwise this section will be rather incomprehensible. Once you understand readily the basic principles of the computational model in the Femtotech essay, it's rather easy to create a close analogy between the quark color charges and the color changing gluons on the one hand, and the quark flavors and the flavor changing W's on the other. You can take the implementation of the NOT, OR, AND gates in the Femtotech essay and substitute the femtoscale set of quark color changes, color changing gluons, for the attoscale set of quark flavors and the flavor changing W's. The analysis is the same for both sets, except that the scale is about 3 orders of magnitude smaller, namely at the attometer scale. We are thus computing at the attometer scale, creating the beginnings of an attotech. To make the above analogy more concrete, make the following substitutions. On the left-hand side of the following list is a component of the Femtotech story. On the right-hand side is a component of the corresponding attotech story. To understand how to implement the NOT, OR, AND gates of the attotech story, simply substitute the right-hand components into the corresponding left-hand side components in the Femtotech story. A red color charged quark corresponds to an up quark. Yeah, a blue color charged quark corresponds to a down quark. A red anti-blue gluon corresponds to a W plus weak force particle. A blue anti-red gluon corresponds to a W minus weak force particle. 4. Zeptotech? Question mark. I had to go to Google to find out the name of the 10 to the minus 21 meter scale. It's a zepto, that's Z-E-P-T-O, zeptometer. And 10 to the minus 24 of a meter is called a yocto, that's Y-O-C-T-O, a yoctometer. I can't say much about a possible yoctotech because very little is known about particle physics at such tiny scales, but there are theoretical models at the zeptometer level. Once the electromagnetic and weak forces were unified into the electroweak force in the 1970s, particle theorists attempted to use group theory to create a grand unified force, or superforce, that is, an electroweak color force, using the special unitary group SU5. Out of this, only partially successful work, came the prediction of two superforce particles that would mediate all the interactions except gravity. Hopefully, string theory will solve the open problem of unifying all the forces of nature. These two superforce particles are called the X and the Y, and have masses about 3 orders of magnitude larger than the W's and the Z. Hence, the range they would operate under would be at the zeptometer scale. Since I don't know how they interact with quarks and leptons, there's not a lot more I can say about a possible zeptotech. 5. X-tech. Having seen above how to implement computing at the femto and atto scales, one can't help but notice that there are commonalities between the two, allowing one to generalize the creation of future X-techs at ever smaller scales, where X is an appropriate level label, for example, nano, femto, atto, zepto, yocto, ... Planck, ? Produce an X-tech. What do you need? Here's a short list. You need A. Stable entities, presumably particles, that have at least 2 quasi-stable states that do not quickly decay or spontaneously change into some other state. For example, with femtotech, the red and blue color charges on the quarks corresponding to the binary states 1 and 0, or with attotech, the up and down flavors of the quarks. B. At least 2 force particles that can be emitted and absorbed to be used to change the states of the entities above. For example, with femtotech, the red anti-blue gluon that changes a blue charged quark into a red charged quark, and the blue anti-red gluon that changes a red charged quark into a blue charged quark. And for attotech, the W plus that changes a down-flavored quark into an up-flavored quark, and the W minus that changes an up-flavored quark into a down-flavored quark. Once you have such basic ingredients, it's fairly easy, at least in principle, to devise logic gates using them to compute any Boolean function. You have computation at the X scale, and hence you have the beginnings of an X-tech. 6. Is smaller faster? I used to be under the impression, and I still am to some extent, that as one scaled down, the greater would be the overall performance of a given level of technology. For example, a femtotech would outperform a nanotech by a factor of 1 trillion. That is, the density would be 1,000,000 cubed times greater, and the signaling speed between the femto components would be 1,000,000 times faster, because the components are 1,000,000 times closer together, because the component giving a total performance increase of 1,000,000 to the 4th power equals 1 trillion times superior to nanotech. A femto machine could flip bits 1 trillion times faster than a nano machine. This huge superiority would put pressure on our future artilects, artificial intellects, massively intelligent machines, to upgrade, actually downgrade themselves from nanolects, that is artilects based on nanotech, to femtolects, that is artilects based on femtotech. Since they will be hugely smarter than we are, they will probably then continue downscaling, assuming that each scaling down resulted in vastly superior performance. But is that assumption valid? Let's do the numbers. The femtotech story in the previous essay uses gluons to mediate the color force. Typically, these color force interactions occur in a time frame of 10 to the minus 23 of a second, and at a range of about 10 to the minus 15 of a meter. That's a femtometer. The attotech story in this essay uses the W weak force particles to mediate the weak force. Typically, these weak force interactions occur in a time frame of 10 to the minus 10 seconds, and at a range of about 10 to the minus 18 of a meter. You may be shocked by the much slower speed of the weak interactions. That is about 10 trillion times slower. So how does that affect the total performance of attotech versus femtotech? Well, badly actually. Of course, the density increase of atto relative to femto would be 1 billion times greater, that is 1,000 cubed. But the much slower interaction speed more than overpowers the greater density impact. So there may be 10 to the 9 times more components per unit volume of attotech matter, but each interaction is 10 to the minus 13 times, or 10 to the 13 times slower. So the total performance increase is 10 to the 9 times 10 to the minus 13 equals 10 to the minus 4. That is 10,000 times inferior. So much for an attotech base based on the weak force. 7. SETI versus SIPI. Does the above analysis throw a monkey wrench into the works of the idea that the hyper-intelligent creatures in the universe that are billions of years older than we are super tiny? Not necessarily. Of course, going from nano to femto is an obvious performance enhancer, because not only is the femtoscale 1 million times smaller than the nanoscale, it uses the color force, one of the fastest phenomena that physics knows about, although Big Bang theory operates on a timescale of 10 to the minus 44 of a second, the Planck time, so maybe there is scope for much faster processes, ? Further research needed here. Inflation, maybe? Sticking with the color force, its essential ingredients, the quarks and the gluons, are essentially point-like particles. They have no known internal structure, so are modeled essentially as points, so could scale down hugely. The only reason the distance scale of 10 to the minus 15 meter is used for the color force is because quarks are usually found bound together in threes, in baryons, like the proton or neutron, which have femtometer sizes. But if an X-tech could be used inside the volume of a baryon, that is inside a sphere of radius of about a femtometer, also known as, aka, a Fermi, then it might be possible to have many quarks and gluons operating in that space and at tiny, tiny scales. Alternatively, one could use gluons alone, since they too are color charged and may interact with each other, forming complex glue balls that function at color force speeds, that is 10 to the minus 23 of a second. It's difficult to talk about such X-techs because the basic physics of how lots of quarks and gluons or glue balls would interact in such tiny volumes, where presumably the quark confinement, stretched rubber band phenomenon, would not be operating, see my earlier essay on this, is poorly known. Our Artilects may be such superb scientists that they may be able to create such an X-tech and hence give themselves the option of downgrading themselves to achieve vastly greater performance levels. Just how far down they could go is an interesting research question. One of my ambitions over the next couple of years is to get so familiar with string theory, now that I am arcing after retirement careering, do what I like, that I dream of creating a string tech. Now the punchline. It should be clear from all this talk of femtotech, attotech, zeptotech, X-tech, etc., that as one scales down, in general, performance levels increase dramatically. Hence, one can readily speculate that any nano-based Artilect, sooner or later, will not be able to compete with his femto-based cousins, and will probably downgrade itself as well. This logic applies all the way down to Planck tech, ? Hence, we come inevitably to the following dramatic conclusion. The hyper-intelligences that are billions of years older than we are in our universe, which is about 3 times older than our sun, have probably downgraded themselves to achieve hugely greater performance levels. Whole civilizations may be living inside volumes the size of nucleons or smaller. When I first had this idea about a decade ago, I chuckled, but now I take it very seriously because there seems to be so much logic behind it. What impact does such thinking have upon SETI, Search for Extraterrestrial Intelligence? Well, I think it makes SETI look rather provincial. I'm not suggesting that the SETI effort should be cancelled, but the above thinking does suggest that the intelligences out there, that is extraterrestrials, ETs, who might be primitive enough to bother sending radio signals to beings like us, are not the most intelligent species in the universe. The really smart ones, I suggest, are very, very tiny. Therefore, I recommend that humanity start thinking about ways to detect their presence. We need a SIPI, a search for infra particle intelligence. For example, why are the elementary particles such carbon copies of each other for each particle type? Once one starts seeing intelligence in elementary particles, it changes the way one looks at them, and the way one interprets the laws of nature, and the interpretation of quantum mechanics, etc. It's a real paradigm shift away from looking for non-human intelligence in outer space to looking for it in inner space, that is, SIPI. That's it. Cheers. Prof. Dr. Hugo de Garis. Email profhugodegaris@yahoo.com. Website profhugodegaris.wordpress.com. YouTube channel name Hugo de Garis. Ciao.